Hello guys, so we are going to continue the discussion with respect to linear algebra. Already we have discussed about transformation. Now we are going to see a type of transformation which is called as linear transformation. First of all, we'll go ahead with the definition. What are the conditions for linear transformation? Then we'll try to probably prove this linear transformation just to see whether a transformation is a linear transformation or not. We'll just try to see based on a particular problem statement. And after that, what we are also going to do is that we're going to understand where all linear transformation is specifically used. So all these things will be covered in this specific video. So first of all, let's go ahead with the definition. So a linear transformation is a function between two vector spaces that preserves the operation of vector addition and scalar multiplication. This means if T is a linear transformation from vector V to vector space W, then for any vectors, it needs to satisfy two important properties. Okay, two important properties. So what this exact functionality or is this definition basically saying? I will consider T as my linear transformation, which is basically transforming a vector V to W. Okay, if it holds these two important properties. The first one is something called as additivity. Okay, so in the additivity, the transformation of any vector u plus v is equal to transformation of u plus transformation of v. Okay, so this is one of the property, and don't worry if you're not able to understand, because I will solve this with a problem statement. Then the second property is homogeneity. Okay, so in the homogeneity, you have nothing but transformation of C of u, where C is some scalar value. Okay, and here you have C T of u. Okay, now let me go ahead and denote what all things that we have. Then for any vector, we will continue from here, u comma v belonging to v. Okay, and any scalar value c, right? If we have this kind of vectors, then we need to probably this transformation needs to satisfy these two properties. Okay, so instead of writing it over here, I will just go ahead and say over here u comma v is belonging to the v vector and c is a scalar value. Okay, scalar value. Now let me just go ahead and repeat it what I have actually written. A linear transformation is a function between two vector spaces that preserves the operation of vector addition and scalar multiplication. This means if T is a linear transformation from a vector space V to vector space W, if this needs to be called as a linear transformation, then it needs to satisfy these two properties. Okay, these two properties. Now when I use u v, it is nothing but we are considering that it is a vector in V, and this specific vector, and this c is nothing but it is a scalar value. Okay, now understand one thing is that similarly you can also apply this in matrices also. Okay, but we'll just go ahead and see with an example, since we are discussing about vector transformation, and this is nothing but linear vector transformation. So let's do one thing. Let's take a simple example and then let's try to prove whether a specific transformation is a linear transformation or not. Okay, so for this particular case, let's take one of the very common example that we specifically use, and it is a real world example which is called as a reflection. Whenever you see in the mirror, right, you probably see your image getting reflected, and you probably see that it is an inverted image itself, right? So similarly, in reflection transformation, if I probably consider this as an example, let's say that I will go ahead and write the reflection transformation. Okay, T, let's consider this transformation across the y-axis maps a vector. Let's say there is a vector which is called as x, okay, and x is denoted by x comma y. So this is a two-dimension vector. So in short, this belongs to a r square, right? Because since it's a two-dimension vector. And let me also provide a transformation that we are going to apply. T of x is nothing but, here we are basically using minus x of y, right? Minus x and y, right? Because this is what is the reflection is all about. So and we are probably we are doing this reflection across the y-axis, right? So if I have that x comma y over here, if you probably go ahead and see this x comma y, I'm actually going to get minus x comma y. So that basically means if this is your any value, it can be x and y. Let's say x and y over here, I'm basically having this value. When I do this transformation, I should be able to get minus x comma y. So this and this. So from this point, it should be coming to this point, right? So if this is x minus y, x comma y, this is minus x comma y. So we are looking for this specific transformation, and this transformation is nothing but t of x, right? T of x, capital X. I'm using capital X over here. And this specific transformation is basically doing the reflection. So from here, it is basically coming to this particular coordinate. It is changing this vector to this coordinate, okay? Or it is transforming the vector to this particular coordinate, okay? Let's do one thing. In order to just show you, right, t of x, I have written x minus x comma y, right? So this is what is my transformation technique. And probably to achieve this, the transformation can be expressed as, so transformation can be expressed as, now how do we achieve this? How do we perform this particular transformation? If I have x comma y, how do I get minus x comma y? So for this, we will take a matrix A, and let's denote this A by minus 1, comma 0 and 0, 1. Why we are using this? Because whenever we multiply, right, if I probably now go ahead and write my t of x, instead of writing this, I can also go ahead and write A multiplied by x. If I do A multiplied by x or A dot product of x, you'll be able to see once I multiply this, what I'm actually going to get. X into minus 1, then you have y into 0. So you'll finally get, see this, I'm going to multiply x into minus 1, right? Then you also have x into 0. So this will basically become minus x, right? Then you have y, because y into 0 and 1 is basically m, right? So we can actually perform a dot operations very much easily over here, right? So I hope you're able to understand with respect to this and you're able to get it. If you're getting confused, let me again do the calculation. Let's consider xy over here, and I'm going to perform a dot operation. For performing a dot operation, what I will do, I will take this. So this is my value. Understand, if I just transpose this, this basically becomes 1 cross 2, and this becomes 2 cross 2. And you know, one of the criteria is that this value and this value needs to be same. So finally, I'll be able to get 1 cross 2. That we have already discussed in matrix dot product, right? So once I do this, x into minus 1, y into 0, right? So it will be minus x, and then you have x into 0, y into minus 1. I'll be getting minus x, okay? So this is what is the transformation that we are able to get. Now let's apply this and see whether this transformation is a linear transformation or not. We need to go ahead and check whether this is a linear transformation or not. Now, in order to check whether this is a linear transformation or not, I will check two rules. One is additivity and the other one is homogeneity. So first, I will go ahead and check additivity. Okay, additivity. Okay, now let's consider over here. Let's say that my vector u is nothing but, it is denoted by u1, u2. Okay, let's consider this. And my vector v is basically denoted by v1 comma v2. Okay, because as I said, this u comma v belongs to v, and every vector u is basically denoted by u1, u2 and v1, v2. Let's this be two vectors. I'm going to consider this two vectors, and this belongs to R square. Okay, now with respect to the additive requirement, the transformation should satisfy these rules. If you are doing transformation with respect to u plus v, I should be able to get transformation of u plus transformation of v. So both this should be equal. If it is not equal, then we can say that, hey, this transformation is not a linear transformation. Okay. So let's do the calculation. So first of all, I will go ahead and calculate u plus v. So u plus v is nothing but I will take u1, u1, u2, and then I have v1 plus v2, right? So once I do this summation, I'm going to basically get u1 plus v1, u2 plus v2, right? So this is my first one. Okay. Now, when I say that I'm going to apply transformation in u plus v, that basically means what? What is transformation? Transformation on x is nothing but we are going to multiply that x, whatever x is over here, right? Whatever function x values are basically holding over here, that by this particular A matrix, and A matrix is minus 1, 0, right? So here what I'm actually going to do, here I'm going to basically take A and multiply by u plus v. Okay. So A is nothing but it is minus 1, 0, 0, minus 0, 1. Okay. I'm basically going to do a dot operation with u1 plus v1, and then you have u2 plus v2. Okay. So once I do this, if you see this, if you do the dot operation, right, you should be able to get u1 plus v1 minus u1 plus v1. Okay. And then you should get the same thing u2 v2. Okay, just do the dot operation. Now I hope everybody knows this, right? How to probably do the dot operation and all. Okay, so it's just like you multiply this element with this with this. So I'm going to get this, right? Otherwise I was doing addition over here, plus 0 only it will become. Then 0 by multiplied by this plus this, I will finally get u2 plus v2. Now here, this is my value with respect to the transformation that I get. Now we need to check whether this is equal to this. So now let's go ahead and calculate transformation of u. Now transformation of u is nothing but here I will just go ahead and multiply u with a, right? So here I'm going to get minus 1, 0, 0, 0, 1, and then you have u1, u2, right? So if I go ahead and do the calculation, it is nothing but minus u1, u2. Okay, again a dot product. And similarly, we'll go ahead and calculate with respect to TV. TV is nothing but transformation on vector v is nothing but a multiplying by v, which is again minus 1, 0, 0, 1. And here I have my vector v1 and v2. Okay. Now when I have this vector v1 minus v1 and minus v1, then 0, then v2. So finally, you'll be able to see that I will be getting minus v1 and v2. Perfect. So overall you got this, right? But on the RHS, what we really need to do, we need to take this transformation, add it with the transformation of v, right? So once we do this transformation, here you can see minus u1 u2 plus minus v1 v2. Okay. So if you do this calculation, it is nothing but minus u1 minus v2, minus v1 and then u2 plus v2. Now see this, whether this is equal to this, right? So if I also go ahead and write this, we can still further write it like this, right? Minus u1 minus v2, u2 plus v2. So here you can see that we have proved our LHS is equal to the RHS. So since LHS is equal to RHS, we can basically say that the transformation technique that we have specifically applied over here, this transformation, this is basically a linear transformation for this specific vectors, right? And this entire means you select any kind of vectors, right? This will probably follow, it basically, again, one more point over here, because we still did not check the second rule. In the first property, it is satisfying. So we are one step towards linear transformation, saying that this transformation basically follows a linear transformation. And this is how you actually do. Okay. So this is what I have actually proved to show you that how you can check whether it follows additivity or not. Now, second one is basically checking homogeneity. Don't worry, I will still take a real world example we'll take some vectors and then again we will try to solve this. So second one that we are basically doing is something called as homogeneity, checking homogeneity. Now for checking homogeneity, let's consider a vector u. U is denoted by u1, u2. Okay. Let's this be a vector in R square and C be a scalar, because the second property is with respect to scalar. Now homogeneity requirement. Okay. Homogeneity requirement is nothing but, it says a transformation with respect to a vector C of u should be equal to C multiplied by the scalar value multiplied by transformation of u. Okay. So we will now try to prove whether this is true or not. So first of all, what we'll do, we will go ahead and calculate C of u. What is C? C, let's consider that it is a vector. So I will just go, it is a scalar. Then I will go ahead and multiply this. So it will become CU1, CU2. Okay. And then if I go ahead and again use transformation of C of u, that basically means I'm multiplying with my A matrix, A multiplied by C of u. When I say multiply, I'm probably talking about dot operation. Okay. Then it is minus 1, 0, 1. And then you will be able to see that I will be having CU1, CU2. If I do this, dot product minus CU1 and CU2. Okay. So this is what we are specifically getting, but still we need to go ahead and compute the right hand side. So this is my LHS. This is my LHS. Now in the RHS, what I really need to do, I need to compute CT of U, right? U, transformation of U. So when I say transformation of U, I will be writing C like this, but along with this, I will, when I say transformation of U, I'm basically taking A multiplied by or dot product by U, right? So it is nothing but C minus 1, 0, 0, 1, and this will be nothing but U1, U2. Okay. So this in turns, if I do the dot operation over here, it will be nothing but C or minus U1, U2, which in turn will be giving me minus CU1 and CU2. So this is my RHS, and both are equal. This are equal. Now, if this is satisfying both, that basically means now I can definitely confirm whatever transformation technique that we are applying, it follows a linear transformation. Okay. See, when we say linear transformation, what exactly it will mean, I will just let you know in some time. Okay. But linear transformation, just by showing diagrams, I will be able to help you and show you that. Okay. Just wait, but understand linear transformation. There is some kind of transformation that is going to happen. It is going to convert one vector to the other in a linear way, right? Linear way basically means it will change linearly itself. Just keep this in mind, because once I show you the diagrams, you'll be able to understand. But for the linear transformation, I have shown you both of the techniques, both of the properties, how it gets satisfied, and we have also checked it out. Okay. Now, let's take one very good example. Okay. And based on that particular example, also you can go ahead and see whether it follows a linear transformation or not. Yeah. And then you may also have a scenario, Krish. Let's say that if you are using this transformation technique, it follows a linear transformation. Show us some transformation techniques that do not even follow linear transformation. Okay. So I will say examples that don't follow linear transformation. So let me just go ahead and consider one example so that you will be able to understand. Okay. So let's go ahead and let's talk about this. Let's consider that I have a vector which is B. Let's say this value is 1, 1. Okay. And my main aim is basically to do a linear transformation of R square and get an R square. That basically means I have a vector U. I need to get a vector V that belongs to R square and all. So here I'm specifically going to apply a transformation. Let's consider that. Let's say the B is defined over here. And what I'm actually going to do, the transformation that I'm actually going to apply is nothing but X plus B. Okay. So this is a transformation. Here B is nothing but it is a vector. Okay. Now let's test for this. So overall, if you go ahead and see, my tx of, or my transformation will be nothing but x plus 1, 1. Okay. This b that you are able to see is something called as fixed vector in this case. Okay, fixed vector. Let's say that I have defined b over here by default, fixed vector. X value can be another vectors itself, right? So let's go ahead and probably talk more about it. Okay. Now, first of all, for this problem statement, we will go ahead and check additivity. Additivity. Okay. Now let's go ahead and check this additivity. Okay. Now in additivity, again, if I want to understand whether this transformation follows a linear transformation or not, this is the rule that I will follow. Probably go ahead and check. I'm going to check a transformation which satisfies this property, right? Now let's consider over here my vector u. So here what we are going to do, let's go ahead and consider our vector u. Let's say our vector u is 2, 3 and vector v is nothing but 4, minus 1. Okay. Now with respect to this particular vector, let's go ahead and do the calculation. So here I'm going to write transformation of u plus v. So first of all, I will just go ahead and use this transformation, and let's take this vector 2, 3. I'm using some numerical values just to show you or prove you, right? So 4 minus 1. Okay. So here I'm going to get a transformation of 6, 2. Okay. The transformation technique that I'm actually going to apply is nothing but this one, right? So if I go ahead and write what exactly is t of 6, 2, it will be nothing but it will be equal to x plus 1, right? X is nothing but x is basically this vector. So here I'm going to write 6, 2. This will be denoted as x. Okay. Plus 1, 1, right? 1, 1 we need to add in this transformation. So finally I get 7, 3. Okay. Now I've got the LHS side. This is basically my LHS side, the transformation after doing this. Okay. On the RHS side, I have to take t of u plus transformation of u plus transformation of v. Now let me go ahead and calculate this transformation of u plus transformation of v. Now if you go ahead and do this, what is transformation of u? So transformation of u is nothing but I will take this vector. What is my vector u? It is nothing but 2, 3. 2, 3. So if I'm applying this transformation, basically the transformation is nothing but 2, 2, 3, and I'm going to add it with 1, 1, right? So this is the transformation that we are specifically doing. And if you see this, it is nothing but 3, 4. Similarly, if you go ahead and do the transformation of, with respect to v, what is my v over here? V is nothing but 4 minus 1, 4 minus 1. So here you will be able to see 4 minus 1, and I am basically adding to 1, 1. This is what our transformation basically means. And here I'm going to get 5, 0. So finally, if I go ahead and do t of u plus t of v, I'm going to get 3 by 4, 3, 4 and 5, 0. And finally, you'll be able to see I'll be getting 8, 0. Okay. So now this is my RHS. And obviously, just by seeing this, my LHS is not equal to RHS. So this transformation does not satisfy the linear transformation, right? But there's still one more condition which we should really need to check. But either one of this, it fails this additive condition, right? So here you can see LHS is not equal to RHS. Did I do correctly? Let's see. So 5, 0. Okay, it's fine. I think. Sorry, this should be 4. I have written it as 0, but it does not matter anyway. But 8, 4. Okay. Now, similarly, we'll go ahead and check for homogeneity, which is my second condition. Homogeneity. transformation of C of U is equal to C transformation of U. So let's go ahead and do this. Let's consider U is my vector 2, 3 and C is some value, scalar value 2. Okay. So if I go ahead and calculate transformation of C of U, it is nothing but I will multiply this C with U. I will be getting a transformation of 4, 12, right? Sorry, 4, 6. 4, 6. Now, once I do this transformation, it is nothing but 4, 6. We are going to add it with 1, 1. Did I write addition in between? Yeah, before. So here this should be addition. Okay. Let's see in other places also I've added. Yes, I've added it. So this will be finally my 5, 7, right? Now this is my LHS. Now let's do for the RHS transformation with respect to U. So 2 multiplied by 4, 6 plus, sorry, it should not be 4, 6. It should be 2, 3 plus 1, 1. I'm going to basically go ahead and do this over here. So let's go ahead and calculate this. It is nothing but 2 plus 1, 3, 4, which is nothing but when we multiply this scalar, it is 6, 8. So here my LHS is not equal to RHS. These are not equal. So obviously it also does not satisfy homogeneity conditions, right? So the transformation technique, I can specifically make a conclusion saying that my T of X transformation, which is nothing but X plus 1, 1, okay, which is a fixed vector over here, is not a linear transformation. Not a linear transformation, right? Because it fails both additivity and homogeneity properties. Homogeneity properties. Okay. So this is one of the very clear example where it does not probably support linear, or it does not satisfy the linear transformation technique.